Hi, we will continue our discussion about the structural loads. By this time, we have the wind load, which is capital W. As you can see in the diagram, uh, we have different sides of the building. The first is the windward side, where the wind is coming. So we call it windward side. On the other side, we call it the leeward side. Okay, so this is very important that you will understand it. The windward side and the leeward side. Uh, the wind usually produces high pressure. That is, it will push the building. And on the other side, the leeward side, the wind will produce a low pressure, which is a suction. Okay, so it will suck the structure. When the wind is entering from front of building, it increases the internal pressure. And take note, the damages due to the wind load usually originates at the corners, under eaves, and at the rates of the roof. So these are the weakness of a building. And normally the wind pressure coming from the left, if this is the the wind, this is pushing the building, but on the leeward side, uh, it is suction. And most of the time, the roof are also in suction. But there are times that the roof near the wind direction, or the where the wind is coming, it can be suction or a pressure. Also, if you look at the plan, it will give you the idea that when the wind is pushing at the front, the windward side, the leeward side is in suction, and also the walls are perpendicular to the wind direction is also in suction. So it's not only uh, in the walls or the windward wall, not only at the leeward wall, not only at the roof, but also at the side walls. So you have to remember that one, that we also have the wind pressure at the side wall. So of course, there are many methods in determining the wind loads, but here we will only talk about the main wind force resisting system according to NSAP section 217B.4. For other structures, you can look at the NSAP because there are a different method for that. Also, there is also a simplified method of computing the wind load. Here we have the enclosed and partially enclosed rigid buildings. The design wind pressure for MWFRS of buildings of all heights shall be determined by the following equation. So this is a general equation in determining the design wind pressure for enclosed rigid building. So the pressure P due to the wind is Q G C sub P minus QI times GCPI. This, and the result is in Pascal. Take note, the terms in parentheses is usually taken as one. So that's why it was put in parentheses. Where the small q is Q sub z for windward walls. Take note, this should be in windward walls evaluated at height z above the ground, meaning the height z is varying from the bottom zero to the height of the building, which is quite different from q, which is qh, because this is for leeward walls, side walls, and roof, which is evaluated only at the height h. Qi is also equal to QH for windward walls, side walls, leeward walls, and roof of enclosed building. So take note, QZ is the windward wall evaluated at height Z, and QH for leeward walls, side walls, and roof evaluated at height H. QI, which is QZ for positive internal pressure, and G as the gas effect factor, and GCPI, the term that I said is enclosed in the parentheses, is the internal pressure coefficient, which can be taken in table 207A.11-1. So here are the steps to determine the MWFRS wind loads. Table 207B.2-1 gives us the steps in determining the MWFRS wind loads for enclosed, partially enclosed, and open buildings of all heights. So as you can see, there will be 7 steps. The first step is you need to determine the category of the building, and then the basic wind speed, and then the wind directionality factor, which are the wind load parameters, the exposure category, the topographic factor, the gas effect factor, the enclosure classification, the internal pressure coefficients, and then later on the velocity pressure exposure coefficients, and you will determine the velocity pressure, the external pressure coefficients, and then you can calculate the wind pressure on the building surface. So here is the step 1, the occupancy category. Table 103-1 gives us the occupancy category. There will be 5 of them: the essential facilities, hazardous facilities, special occupancy structures, standard occupancy structures, and miscellaneous structures. I want you to go over the occupancy or function of the structure so that you will be able to determine what occupancy category your structure. Also, step 2, we need to determine the basic wind speed. Depending on the occupancy category, like for example, if you are designing a hospital is actually essential facility, that is one. Uh, so if it is essential facility, then you have to look for the figure which is on the right, that is for occupancy category 1 building and other structures. If in Bukidnon, you will see the wind velocity is around between 280 and 300 kilometers per hour. So that's 290 kilometers per hour. And as you can imagine, those islands or areas near the Pacific Ocean, it has a larger or a higher uh, wind speed. That's around 310, 320, I think. Yeah. But for other category, for occupancy category 3, 4, and 5, it has a lower wind speed. Like for example, in Bukidnon, that's between 270 and 280. So that's 275 compared here 290. There's a big effect on that. So you need to consider the the area or the location of your structure in determining the basic wind speed. Also, step 3, we have the wind load parameters. So for the wind directionality factor, that is key sub D, there is a table here that gives us the value. For main wind force resisting system for a building, you can see the value is 0.85. Also, for the exposure category, you can determine first the surface roughness. It can be B, C, or D. And then you can determine the exposure categories: exposure B, exposure C, and exposure D. So for open terrain or the flat country, it is surface roughness C, which corresponds to exposure C. Take note, exposure C shall apply for all cases where exposures B or D do not apply. Also, we have the topographic factor KZT. This is the wind speed up effect shall be included in the calculation of design wind loads by using the factor KZT. Using this equation, which is KZT is equal to 1 plus K1 plus K2 plus K3 to the power 2. There is a table for these factors K, but take note, if site conditions and locations of structures do not met all the conditions specified in section 207A.8.1, then you can just use KCT is equal to 1.0. Here is one of the table for the topographic multipliers, like for example for exposure C. Aside from that, we have the gas effect factor G. The gas effect factor for a rigid building or other structure is permitted to be taken as 0.85. Also, the enclosure classification, it can be open buildings, partially enclosed buildings or enclosed buildings. For the meaning of this, you can read on NACP the technical definition of these three classifications. For the internal pressure coefficient, GCPI, uh, we have values here depending on the enclosure classification. So it's important that you will be able to classify first the enclosure classification. For open buildings, that is zero because it's internal pressure. So since open, no, there will be no internal pressure. For partially enclosed buildings, it can be plus 0.55 or minus 0.55. For enclosed buildings, that plus 0.18 and minus 0.18. So as you can see, there are two values, and it's higher for partially enclosed building. For enclosed buildings, normally the assumption of the wind is just on the surface of the building, and it has a lower value. This is applied for walls and roof. For the velocity pressure coefficient, pressure exposure coefficient, you can just use this table 207b.3-1, depending on the exposure of your building and the height above the ground level. This is the height Z that we are talking earlier. It can be Z is equal to 0 up to a certain height, and then, like for example here, 0 to 4.5 meters, and then 6 meters, 7.5. If your value or if your height is not within these values, you can just use interpolation. Okay. For the velocity pressure uh, evaluated at height z shall be calculated by the following equation. So if a certain height z, you need to calculate for every height. Okay. So from 4.5, 6, and so on to 7.5, then 9 meters, you have to evaluate it in every height z. The velocity pressure is defined as QZ is equal to 0.613. This constant factor was used because of some derivations, and it needs some factor. Uh, it, it should be multiplied with Kz, the velocity pressure exposure coefficient, the Kzt, the topographic factor, Kd, the wind directionality factor, and the velocity of the wind, the basic wind speed V. Then you have to square it. So take note, the velocity pressure actually it increases rapidly if your velocity or the basic wind speed is quite high because it is squared. Take note, Q sub z should be in Pascal and the velocity should be in meter per second. So the 275 kilometers per hour should be converted first to meter per second. Otherwise, it would be a really large value. So here are the external pressure coefficients. According to this diagram, for a gable hip roof, of course, it depends on the structure. This is only for the hip roof, the gable hip roof. So for this particular structure, you will see the direction of the wind pressures. And to determine the value of CP or CN, you need to use this table. It depends on the length and this one the in the plan, if this is the windward side, the dimension of the building perpendicular to the windward side is B. The parallel is L. Take note about these notations. This is L, and also the height Z, and the mean height of the building at the mean roof height, that's H. So ang EDS gani is a main roof height. Dito ka magkuha sa roof dapit. Dili sa pinakatumay but the middle of the roof. So it depends on the surface. If it is windward wall, leeward wall, and the side wall, and depends on the ratio of L over B, you will get the value of CP. Yeah. And also the roof pressure coefficients, because this is only for wall pressure coefficient. For the roof pressure coefficients, you can use this table. It depends on the slope of the roof, and then the mean roof height H over L and the corresponding angles. Okay. Then the last step, step 7, is to calculate wind pressure P For the enclosed or partially enclosed rigid buildings, you can use the formula. I have presented this already. But the other formula for enclosed and partially enclosed flexible building, this is quite different. The first formula is for rigid buildings, the other one is flexible. They have almost the same formula, except for the first term we have GF. G sub F is different from G. For open buildings with monoslope pits or true pre-roof, P is QH times G times CN. This is expected because for for open buildings, the GCPI is equal to 0, as we mentioned earlier. So the remaining term will be the first one. So actually, as I have said earlier, the first equation is the general equation for all of the wind loads computation. Okay? So also we need to apply a minimum wind load. If your computed wind load is lower than the minimum wind load, then you have to use the minimum wind load specified by NECP. The minimum wind load should be 0.77 kilopascal, which is to be multiplied by the wall area of the building, and it's around 0.38 kilopascal to be multiplied by the roof area of the building projected onto the vertical plane. Take note, the design wind force for open buildings shall not be less than 0.77 kilonewton per meter square to be multiplied by the area EF. So you can see how it will be applied in a certain building. It will always include the roof. As an example, we have adapted an example from Hibbeler. uh, because I changed some of the units. The units is in English units, and I just converted it into SI units. Again, we have to be very flexible. So here we will be interchanging using either the English units or the SI units. We have an example assuming that the enclosed building is used for storage purposes and is located in Baguntaas, Valencia City on open flat terrain. Open flat terrain means the surface roughness is C, so that the exposure is also C. When the wind is directed as shown, determine the design wind pressure acting on the roof and sides of the building using NECP 2015 specification. For this particular example, the wind is coming from this portion, Kinesia diri. But in reality, winds can be coming from the other side or the front side or front elevation of the building or the rear elevation or at a certain angle. Uh, so when you are designing, you need to consider all these directions. But for this example, we will only determine on the side of the building. So here is the solution. We have to follow the 7-step procedure. For step 1, we have to determine the occupancy category. Since it's a warehouse, it's for is occupancy category for standard occupancy structures, and the basic wind speed at Valencia City, as we determined earlier, is actually 275 km per hour. That's around 76.39 meter per second. Again, remember, do not forget to convert the basic wind speed into meters per second. Step 3, for wind directionality factor, we use 1.0. Take note, since only wind loading is being considered, but in the table, the value is 0.85. So here we use 1.0, but if we have to combine it with the other loading, you will be using KD to be 0.85. Also, we have the exposure category for open flat terrain. The surface roughness is C, thus the exposure is C. The topographic factor, since it's quite flat, KZT is 1.0. The gas effect factor G is 0.85. Enclosure classification is enclosed building because it's a warehouse. And the internal pressure coefficient GCPI is plus minus 0.18 for walls and roofs for all heights. Take note, there are two values of here, positive 0.18 and negative 0.18. So the resulting wind pressure will be two sets of wind pressure. Step 4, velocity pressure exposure coefficient. take first the roof height, then take the middle of it. Its prime is 3.94 m, so that the mean roof height is the height of the building 7.5 meters plus one half of the height of the roof, 3.97 divided by 2. So the main roof height adds is equal to 9.48 meters. So you can use the ratio and proportion or interpolation to determine KZ at the height 9.48 meters, because you cannot find this one in the table that I have presented. The result is 0.9896, or approximately 0.99. In step 5, we can now compute the velocity pressure of QZ or QS. So here we apply the different values of the factor. QZ is 3.54 kilopascal. Okay. So step 7 or step 6, external pressure coefficient CP can be determined from the figure 207b.4-1. And the step 7, we can compute the wind pressure P for enclosed rigid building by substituting the necessary data. So here, P is equal to 0.85 QCP minus plus 0.64, because there is a subtraction in the second term. So the terms nga positive, negative 0.18, mabalhin na rin siya. It will become 0.85 QCP minus plus 0.64. Okay? So the pressure loading are obtained from this equation using the calculated values for Q, Z as listed below in accordance with the wind pressure profile of figure 207b that 4-1. So this is the wind pressure equation that we will be using. So we will be changing according to the value of Q and the value of CP. First, we need to determine the value of Q for a particular height. So for windward wall, windwards attack, here the pressure varies with height Z. Since QZ GCP must be used. For all values of L over B, CP is 0.8. So that from the equation of P, from the height 0 to 4.5, look at the table. We have Q, which is 3.01. Oh, sorry, this is 3.01. Nasayop ko ani. This is 3.55 because earlier I used 0.85. So sorry for that. So change Q to 3.5 here. I think the value should be almost the same, or there is actually sorry, sakto de because we are using this table Z 0 to 4.5 with KZ and QZ 3.01. That's the 3.54 is for a height of 9.48. Sorry for that. For 6, 3.19, 7.5, 3.33. So that's why here the computations at 0 to 4.56 and 7.5, we have different values of QZ. So here the results are 2. From 0 to 4.5 meters, 1.41 kilopascal or 2.69 kilopascal. For 6 meters, 1.53 and 2.81. For 7.5 meters, 1.62 or 2.9. For the leeward wall, according to the ratio L over B, which is equal to 1, so CP is zero point 0.5. Again, look at the table that I have presented to you. Then also for Q, which is equal to QH, and so P is 0.85, 3.54 times 0.05 negative plus or minus plus 0.64, so it will give us two values, which is suction. Since the result is negative, it is suction. Minus 2.14 kilopascal or minus 0.86 kilopascal. The side walls for all values of L over B, CP is minus 0.7, and therefore since we must use Q is equal to QH, we have this value. Take note, we are using the roof mean height, not Z. P is equal to minus 275 kilopascal or minus 1.47 kilopascal. For the windward roof, here we use the main roof height H over L, which is 0.211, which is less than 0.25, so that the value of CP is or minus 0.7. Again, you have to look at the table to determine the value of CP. So that P here is minus 2.75 and minus 1.47. Again, which is suction. So you have to check also with the minimum wind load, which is 0.77. Accordingly, most of the pressures are above, or all of the pressures are above 0.77. So this is okay. In the leeward roof, in this case, CP is minus zero point 0.3, and therefore with Q is equal to QH. So we get the value of P, which is minus 1.54 kilopascal, or minus 0.26. Here, minus 0.26 is lesser than 0.77. So this is not included because the minimum should be in the windward side. Okay? Ang windward side above the minimum values man. So after that, here are the two sets of loadings on the elevation of the building, representing either positive or negative internal building pressure. The main framing structure of the building must resist these loadings, as well as for separate loadings calculated for wind blowing on the front or rear of the building. So I just summarized this one, the result in this diagram. So as you can see, it's really a simple idea actually, but you need to calculate a lot of things. Okay, so that's all for the wind loading. Thank you.